problem: how to get a $10 million, one-of-a-kind, largest-in-the-world telescope mirror up to the top of a 10,500-foot mountain peak in one piece on a road that was built by the WPA in the 1930s. That was the problem faced by Precision Heavy Haul Incorporated of Phoenix, Arizona, when they agreed to transport two major components of the Large Binocular Telescope from the Mirror Lab at the University of Arizona in Tucson, Arizona, to the LBT enclosure at the top of Mount Graham near Safford in southeastern Arizona. The components were an 8.4-meter diameter parabolic mirror and the mirror cell, which will support the mirror on the telescope. The mirror, the largest in the world, was the first one of two that would be transported to the mountaintop and placed in the Large Binocular Telescope. The telescope will be the largest in the world. When completed, this telescope will be nearly 10 times more powerful than the Hubble Space Telescope. When the LBT is fully operational, it will be the world's most powerful optical telescope, capable of imaging planets beyond our solar system. It will allow astronomers to peer deeper into the universe than ever before. The mirror, 27.5 feet in diameter, 3 feet thick, and weighing 18 tons, is not self-supporting. For transportation purposes, it was supported in a special box having some 280 pneumatic actuators that restrain and cushion it in every direction. The mirror and box together are about 30 feet 1 inch square, 9.5 feet thick, and weigh about 55 tons. The cell, which will support the mirror on the telescope, is about 29.5 feet in diameter, 9.5 feet thick, and weighs about 50 tons. The mirror is very expensive, required years to produce, and is quite fragile. Therefore, the university designed and built a dummy mirror out of steel that closely models the real mirror in size, weight, location of the center of gravity, and stiffness. Every operation that was to be performed on the mirror had to be first performed on the dummy mirror, thus allowing a check on the adequacy of the mirror box and the transportation and handling systems. The route from Tucson included 122 miles of interstate and state highway to the base camp near Safford. Precision loaded the mirror transport box and its precious cargo at U of A's Mirror Lab, which is located in the campus football stadium. The mirror-carrying convoy pulled out of the lab hours before dawn, accompanied by 25 police escort vehicles from various agencies. The police escorts were arranged and coordinated by the University of Arizona Police. The car and motorcycle escorts formed a rolling blockade as the mirror traveled down I-10 and State Highway 191. These officers provided both traffic and mirror safety as the convoy averaged 45 miles per hour to the MGIO base camp at the base of Pinaleno Mountains. When the team arrived at the base camp, they had another 29 miles up the tortuous Swift Trail to the mountaintop. This last 29 miles averages more than 5% grade over the entire length, with some areas as much as 12%. There are numerous switchbacks, with extremely short radii and lateral slopes up to 22%. In fact, 523 curves and switchbacks were noted. The Tucson to base camp portion of the haul utilized a 9-axle trailer, with load beams high enough for the loads to clear roadside obstacles. The Mount Graham portion of the road is much too narrow to accommodate the components loaded in this manner. Most of the road was a side hill cut, with the bank on the right and the canyon on the left. If the loads were tilted up on the right-hand side through an angle of 60 to 70 degrees, they best fit the mountain profile. At 60 degrees, the loaded height was 33 feet, the width 21 feet 3 inches, and the center of gravity 17 feet 10 inches above the ground. The problem remained one of providing equipment that would sustain that position, maneuver and level as required, and provide a comfortable factor of safety against overturning. The road and load requirements made it obvious that a European platform trailer would best fulfill our needs. A 6-line Goldhofer was selected for its capacity, stability, and maneuverability. The 12 axles are normally grouped into 3 sets of 4, in a triangular distribution that allows the trailer to negotiate warp surfaces without significant effect on the individual axle loads. Alternatively, they may be grouped into 4 groups of 3 in a rectangular load distribution. This configuration has approximately 50% greater lateral stability against overturning than the triangular distribution, but introduces the problem of axle groups on opposite corners tending to take the entire load on warped surfaces. This tendency is modified by tire deflections and twisting of the trailer frame, and more importantly, by manually adjusting the hydraulic pressures in the 4 groups. center of gravity and large cross-section made the load very susceptible to overturning from side slopes or wind loading or a combination thereof. The 4-point loading configuration was, therefore, accepted along with its operational problems. It was noted that additional stability could be gained by adding counterweight to the loaded configuration and placing it as low as possible, thus lowering the combined center of gravity. The amount of counterweight was determined by subtracting the weights of the load, the support frame, and the trailer from the rated capacity of the 6 axles on one side. Thus, 70,000 pounds of steel plate was placed on the trailer deck, lowering the combined center of gravity by 2 feet 10 inches. This final configuration had a lateral overturning angle of 16.6 degrees, an increase of 107% over a 3-point system without counterweight, and 30% over the 4-point system without counterweight. It also has a safety factor of 2.6 against overturning from a 75-mile-per-hour wind. The support frame on the trailer had to accommodate both the mirror box and the cell. They varied approximately 6 inches in length, and hardpoints to which supports could attach varied by 10 inches in the lateral direction. The longitudinal difference was accommodated by designing bolted trunnions that were sufficiently strong to support the load over a substantial length. The actual attachment to the trailer needed to be easily connected during loading and unloading, and yet meet the special requirements of each load. One problem was that the 4 supports on the loads were fixed with respect to one another, as the loads are quite rigid. The support points on the trailer, however, could vary substantially from one another, as the loads on the 4 axle groups varied with the road conditions and corresponding hydraulic adjustments. The trailer and support frame were quite limber, and the loads were quite rigid. Power for the moves was provided by a new Kenworth tractor with special low-speed rear ends towing and a Caterpillar 980 front end loader pushing. They worked well together at speeds varying from less than a mile per hour to 3 or 4 miles per hour. The 4-point suspension system was less sensitive than expected, and the trailer operator was able to maintain pressure and level conditions within acceptable parameters with very rare stops for corrections. These happened most often on the unpaved portion of the road, where there was significant washboarding of the surface. In these areas, 3 undulations of washboarding corresponded roughly to the axle spacing, and the amplitudes of oscillation about the longitudinal axis tended to build up quickly. When forward motion was stopped, the system returned to normal in 10 to 15 seconds. Experimentation showed that slightly increased speeds improved the performance in these areas. In general, the equipment behaved as planned, and the work was completed on or ahead of schedule. The challenges faced by Precision Heavy Haul and the LVT team were formidable. This project was successful because of the dedication, skill, and knowledge of many individuals. Their expertise and teamwork made this very difficult project possible.